Well, thank you for joining us today for another talk at the Origin Seminar. It's a pleasure for me to introduce today's speaker, Enrique Vázquez-Semadeni. He's a world expert in MHD compressible turbulence and thermodynamics in the interstellar medium, and in how these processes shape molecular clouds and star formation. He also worked deeply on gravitational collapse, showing that it is much more complex than we often assume, as he will tell us today. He obtained his PhD from UT Austin in 1991 under John Scalo, with a thesis on interstellar turbulence. That same year, he joined the Institute of Astronomy at UNAM in Mexico City, later moving to its branch in Morelia, now the Institute of Radio Astronomy and Astrophysics, IRyA. He became full professor in 2007 and served as director of IRyA from 2015 to 2019. He has received several awards, including the Research Prize of the Mexican Physics Society and the Research Prize in Exact Sciences from UNAM. So thank you, and go ahead, please.
Well, thank you very much, Grace, for the introduction, and it's a pleasure to be here. Thanks a lot for the invitation. Great opportunity to talk to you a little bit about what we've been learning in the last several years, actually, about gravitational collapse, and which turns out to be a lot more fun than we normally think about in graduate school, and the way we model it very often. And I would like to take the opportunity to mention that this talk is going to be mostly based on one of the chapters of my recently published book on interstellar flow and star formation. And in that book, I try to give the basic physics underlying molecular cloud formation and star formation, trying to go a little bit beyond the standard, the classical examples that we study in grad school and so on. So in particular, I look a lot at the virial theorem out of equilibrium situations in the presence of accretion. I'll be talking a lot about accretion today. And also how the virial theorem should be used when we are dealing with turbulence, with driving and dissipation and so on and so forth. And a lot of what we're going to hear about today is in the chapter on gravitational collapse on the book. So I hope it's useful because to me it was a lot of work. So anyway, this is a list of the collaborators that have participated in the work I'm going to be showing today. Several of them have been my grad students. Griselda was also my grad student, and but her work in particular is more advanced than what I'm going to talk about today. So the outline of this talk is that first I would like to convey the notion that collapse sets up a flow. It's not just an isolated event. And with that picture in mind, then I would like to go into the prestellar stage of gravitational collapse and how that happens in an outside-in fashion rather than the inside-out that we often think about. Then I'll go into a discussion of how the density profile, the radial density profile, of course, evolves, and also how the accretion rate evolves. And then into how collapse of different of turbulent density fluctuations inside large objects undergo like a sequential onset, going from larger to smaller mass scales. And then I'll go into a very interesting part which refers to the fact that both cores and their stellar mass content grow their masses over time. So their masses increase simultaneously, and that has a lot of implications, interesting implications. Then if for a miracle I manage to have enough time, I would like to talk about anisotropic collapse and the evolution of the energy budget in collapsing regions, but I don't think I'll have time to do that. So anyway, let me start with this collapse term that we often use, but often in a misleading fashion. And so I went out and looked at the definition of collapse in the dictionary. And of course, we all know it as a verb, and it says to fall or shrink together abruptly and completely, fall into a jumbled or flattened mass through the force of external pressure. Or as a noun, it is a breakdown in vital energy, strength, or stamina. So in general, it sort of conveys the idea of a sudden sort of event, a sort of deflation. In astronomy, we use it also oftentimes as a sudden event and localized in space. However, when we look at analytical and numerical solutions of the equations, what we see is that we obtain a flow, and a flow that spans a wide range of scales. And so that's what I will be talking about today. So I would like to start way back at the beginning at the theory that was performed 60 years ago by Larson and and his contemporaries like Larson, Princeton, Hunter, Shu, and that is the discussion of gravitational collapse under a similarity analysis, and oftentimes under isothermal conditions, and of course in spherical geometry. So this is the simplest case that we can consider. And this analysis is performed in terms of what's called a similarity variable, which we will denote psi, and it is the radial dimension divided by the temporal dimension multiplied by the sound speed, cs. So this is a non-dimensional variable which essentially measures radial distance, but the unit is evolving in time. So it's a sort of co-moving coordinate, if you want to think about it in those terms. And so, to me, the paper that actually summarizes all of the possible solutions about gravitational collapse is that by Whitworth and Summers in 1985. Unfortunately, it's not such a highly cited paper. And I think it's partly because it's very mathematically intricate. And so part of what I try to do in my books chapter was to try to put it in terms that we astronomers can understand. And so basically, Whitworth and Summers in 85 discussed the gravitational collapse and looked at the asymptotic solutions very close to the center and very far from the center. And so they found that these asymptotic solutions contain two spatial regions, an inner region, which we can think of as a core, and an outer region, which we can think of as an envelope. And then it has two temporal stages, an early time, stage, which is characterized by a negative time. It's described mathematically with negative times. And the late stage, which is the protostellar stage, which is described as the positive part of the time dimension. And these two parts are separated by the formation of a singularity, which for us is a protostar. And this is assumed to happen at t equals 0. And each of these stages and regions are characterized by their own specific density and inflow speed profiles, radial profiles. So during the prestellar stage, that is negative times in the mathematical description, we have to keep in mind that, of course, there are no stars there yet, so only the self-gravity of the gas is important. We oftentimes think just in many of the accretion studies, the inflow studies that we think about are consider only the gravity of the central star. But that's, of course, that cannot happen before there's any star there. So the prestellar stage of the collapse is totally controlled by the self-gravity of the gas. And like I said, it consists of an inner region, which, for example, is this central part here. This is the density and the velocity profiles versus this non-dimensional variable, which is essentially the radius scaled by time. And so in the inner part, you have a uniform density. It's characterized by a uniform density and an inflow speed, which is negative because it's pointing inwards, which is proportional to the radius. So it grows linearly with radius. Then again, there's the outer region corresponding to to values of psi greater than unity. And these are characterized by an r to the minus 2 density profile and an infall speed which has these asymptotic terms, a constant term, which is the one drawn here. So if this constant is non-zero, then the infall speed at large distances goes to a uniform value. And then if you impose that the velocity at infinity has to be zero, then the next order term is inversely proportional to the radial distance. So it would fall like this in this plot. Then there's the protostellar stage, so corresponding to positive times, and there the inner region is dominated by the gravity of the central star. So in this case, you have the classical shoe profile with a density that goes like r to the minus 3/2, like here, and an infall speed that goes like r to the minus 1/2, like here. And then the outer region, which is dominated again by the self-gravity of the gas. So very far from the star, the stellar mass is negligible, and what dominates is the gravity of the gas again. And so you get the same profile as in the prestellar outer region. So rho goes like r to the minus 2, and v goes like a constant minus an inverse term in radial distance. So there are a few things to note about these asymptotic solutions. First is that the inner region of the prestellar stage is actually not self-gravitating. Instead, it can be thought of as just being compressed by the large-scale infall. So if you look at this part, it has a flat density, and that is precisely the result that, for example, material at this position does not feel sufficient gravity from the inner part, and so this entire region can be just thought of as being in pressure equilibrium with no significant gravity. Gravity only begins to be important here, and this is where you need then to reduce the external pressure and therefore the external density, so that both the pressure and the gravity maintain the equilibrium, and as in a Bonner-Ebert sphere. So here, this sequence, this brings me to the next point. The prestellar collapse stage is actually very similar to Bonner-Ebert profile that has its flat part, flat inner part, and an r to the minus 2 part in the outside. So why is that? It's essentially because the prestellar stage amounts to a sequence of Bonner-Ebert spheres under increasing external pressures. So you can picture the prestellar stage as a temporal sequence of Bonner-Ebert spheres with increasing external pressure until you reach the singularity at the center. Another point to keep in mind is that the prestellar collapse occurs from the outside in, inside the initial Jeans length. And so I don't have time to show it here, but you can think of this unity value for the non-dimensional variable as being of the order of the Jeans length for the central density. So the size of the inner region is of the order of the Jeans length for this density, which is precisely consistent with the fact that the material very close to the center here is not really feeling any strong force from gravity, from the internal gravity. So it's just pressure confined. But then the collapse, then the velocity at the central part is increasing radially. So the largest speeds occur around this position here, precisely positions on the order of unity of the non-dimensional variable, which is of the order of the Jeans length here. So what that means is that the physical region with large velocities now is approaching the center, because as time goes on, remember that for the prestellar stage, the time is negative. So the time is going from minus infinity to 0 during the prestellar stage. So, but in magnitude, the time is decreasing. So as you go from minus infinity to 0, time is decreasing. And so to keep this position at unity, you need to make the radius smaller and smaller as together with the time. So that means that this point in physical space is actually moving towards the center. So the physical position of the large infall speed region moves inward as it approaches the singularity. So this amounts to outside-in collapse. It's sort of like a tsunami falling onto the center. Then finally, at t equals 0, when this finite speed reaches the center, you develop an infinite slope here for this point, for this region, sorry. And then you develop a shock at the center at the same time that you develop a singularity, because you have brought a finite amount of mass into an infinitesimal volume. So that means that during the prestellar collapse, the collapse is happening from the outside in with inside the initial Jeans length. That is, the collapse propagates inwards from the Jeans length. But this is kind of strange, no? Because we have been taught in school that Schu's famous solution talks about an inside-out collapse. So how does this happen? And what happens here is that Schu's solution was a very special sort of solution. It was a very specifically chosen solution that assumed that the initial condition was a singular isothermal sphere. What is a singular isothermal sphere? It's just an r to the minus 2 density profile all the way from the center to infinity. This it's called singular because it contains the singularity at the center, which means that the density divergence at the center, that diverges at the center already. So essentially, Schu considered the start of the collapse starting from the protostellar stage. He entirely neglected the prestellar stage. And so in this case, you get this, the famous Schu regime, which has a rho density profile that goes like r to the minus 3 halves, and an infall speed that goes like r to the minus 1 half. And then outside of the infalling region, you have 0 speed. And this is the reminiscence of the initial hydrostatic condition. But unfortunately, the singular isothermal sphere cannot occur in reality. Why? Because it's far beyond the threshold for instability for Bonner-Herbert spheres. We know that Bonner-Herbert spheres become unstable when the central density becomes larger than about 14 times the external density. But a singular isothermal sphere has a diverging density at the center, so it's infinitely denser than the outer part, the outer boundary of the sphere. So the singular isothermal sphere is, you could say, it's the most unstable Bonner-Herbert sphere, meaning that if you start with any realistic finite central density configuration, it will have been collapsing for much longer than for a much earlier time than when the singularity occurs, right? And so that is what happens. Any realistic initial condition must have started to collapse long before the singularity develops. And well, I can skip this part, but this is just showing that when you start, this is a plot that shows, again, these are velocity profiles. These are velocity profiles close to starting from the singular isothermal sphere. And so the velocity outside vanishes. But when you start far from the singularity, when you start with a typical Bonner-Herbert sphere with maybe just unstable, then the infall speed is certainly finite, way beyond this radius. So then this inside-out solution, where the outside is just hydrostatic and the inside is infalling, is only true mathematically when you choose the singular isothermal sphere as an initial condition. But when you choose any other realistic situation, then you have collapse ongoing to arbitrarily large distances, although perhaps with a decreasing velocity, perhaps with an r to the minus 2 density velocity profile over here. So realistic solutions have non-zero infall speeds beyond the sonic radius, and this is consistent with observations. It has been observed from 25 years ago. So that's as far as the hardcore theory for spherical collapse is concerned. And then, oops, sorry, I moved. Now I would like to move to to non-self-similar evolution, because after all, we're concerned with how density fluctuations inside the cloud, which these density fluctuations are most likely of turbulent origin. So, but at some point they begin to collapse. They begin to contract on their own self-gravity, and so we're interested in understanding how this happens. So, like we all know that the self-similar solutions apply far from spatial boundaries and far from the initial conditions. So, but when an object is just starting to collapse, how does it evolve? And that's what we would like to ask. And so for this, we would like to study the early transient evolution of prestellar collapse. And this is what we did in a paper in 2021, and it's also summarized in the collapse chapter of the book. And it refers again to idealized isothermal spherically symmetric collapse. But now we're going to give up the assumption of self-similarity, and we're just going to start from essentially nearly uniform density initial conditions. We will consider only the collapse of the region that spans one G's length in my initial uniform density. So let's assume that at time equals 0, I have just a nearly uniform initial density, perhaps with just a perturbation here, so that it triggers the collapse of a G's length sized object. And then, of course, it must become more and more centrally peaked, like in the classical early solutions of Larson in 1969. So these are snapshots of his simulations back then, showing that you develop this typical prestellar profile with a flat central density and an r to the minus 2 outer density, but then you can model this as a single power law with increasing slope. Then this is what we will do here. Just assume the density profile is always a power law. This is admittedly not realistic. It's a first approximation for how the material concentrates into the center. And then we will make another assumption, which is that the gravity at any point, at any radial point along the profile, is given by the gravitational force of the central of the material inside that region. So at a given radius r here, my speed is just from an energetic consideration. My speed is given by the square root of gm over r, where m of r is the mass internal to this radius. And so we just assume that the velocity is, that the gas picks up velocity, and then, of course, it begins to drag in material from the outside, and so this generates also an accretion flow onto the core. So now, if we introduce this power law density profile into the continuity equation of gas dynamics, then interestingly, we can come up with an equation for the rate of change of this of the slope of the density profile. And so this is what you get if you do that, and you also insert the form for the velocity. And it's got, this sort of complicated form, but this is just a number. This is some form of radial dependence, which is telling us that indeed our approximation of a single power law is not perfectly correct, because it does depend on radius. But let's for now forget about that, and let's focus on this coefficient here. This coefficient here tells us that, as you can see, that this coefficient here is positive if p is less than 2. And that means that the time rate of change of the slope of my density profile is positive. So if p is less than 2, then p increases. On the other hand, if p is larger than 2, then this coefficient is negative, and then p decreases. So we have that here. So what that means is that p equals 2 is an attractor for the density profile slope. That means the density profile slope wants to go to that value. It wants to reach 2 and then stay there. And this is very interesting. I first saw it in this paper by Wangxing Li in 2018. Not this discussion, but the fact that that the slope of 2 has a very interesting property, which is that it preserves the accretion rate as a function of radius. The accretion rate is independent of the radius. But the very interesting point here is that then the gas, your collapsing object, wants to go to a slope of -2 without the need for any initial subsonic condition, as Frank Shu postulated in 1977. He tried to explain the generation of the slope of -2, looking at the problem from the point of view of Bohr-Herbert spheres, which are in hydrostatic equilibrium at all radii. And so at large radii, you need to balance gravity with the external pressure. And that is what gives you the r to the -2 profile for hydrostatic configuration. And then from there, Frank concluded that you needed a subsonic initial inflow condition so that you could have pressure waves traveling around your core, maintaining this pressure balance everywhere in your system. But this argument actually shows that the slope of -2 is actually an attractor. The system wants to go to this slope, and this is just an effect of gravity and spherical symmetry. So as long as you have spherical symmetry and just gravity acting, the system wants to develop a slope of -2. So you don't need the subsonic stage that Frank Shu postulated. And that was the reason to assume that you needed to start with something very close to being hydrostatic. So you can have dynamic contractions from early on, and the system will want to go to a slope of -2 anyway. So now, the funny thing is that in reality, cores appear to saturate at somewhat shallower slopes than -2. In this same paper, we collected the reported slopes for various star-forming cores, and we found that, for example, for low-mass cores, the reported slopes peaked at about -1.9. For high-mass cores, the reported slopes peaked at about -1.7. But in any case, of course, there were a few cases of reported slopes steeper than -2, but the bulk of the cores seem to have slopes of shallower than -2. So something which we don't fully understand yet is keeping the cores from actually reaching this attracting value of -2. But in any case, this actually has some very interesting consequences, as we will see. Now here, let me come back to the accretion rate. The accretion rate across a spherical shell of radius r is given by this expression, which again sort of looks complicated, but this is just a number again. The accretion rate is just the mass flux, rho times v, the density times the velocity at every radius. This is the mass flux, so mass per unit time per unit area, times the surface area of the sphere, 4 pi r squared, and that gives you the total accretion rate at radius r. And again, so here you see that you have this exponent here, which means that if p is less than 2, then you have a decreasing mass flux rate inwards. What does that mean? Okay, for if p equals 2, then this is independent of radius, right? Because this cancels out, we have the zero exponent here, and this is radius independent for p equals 2. That was Wangxing Li's result from 2018. But what we found afterwards is that if p is less than 2, then your accretion rate decreases inwards. And that's what's happening in all of these cores, because all of these have slopes shallower than -2. Uh-huh. So that means that the accretion rate is decreasing inwards, and that means that the gas sort of stagnates as it moves inwards. Uh-huh. We in this paper we termed this phenomenon gravitational choking. We called it gravitational choking. The gas just sort of stagnates as it flows inwards, and this allows cores and clouds to grow in mass. This is super interesting because if you have an r to the minus 2 slope, then you cannot have the core growing because all of the mass that you feed into the core gives into the stars at the center. So there's a continuous, the same mass flux going through at the outer edge and at the inner edge, and so the core is just static. But if the flow stagnates in along its way, then the core grows. And this is, well, an interesting comment is that this is a purely gravitational effect. No need for feedback here. And this is just a result of the fact that gravity cannot keep pulling the material inwards at the same pace at all radii. It's sort of gravity losing its stamina as it goes inwards, and so the gas is just left there. And so central regions increase their density. This means that the clumps are increasing their density and the system increases its total mass. Okay. But this also explains what we have observed in numerical simulations. We have observed that the clouds grow over time. So in this paper from 2020 with Vianney Camacho as the first author, we looked at a cloud in some simulation of turbulence in the ISM in general. And so this cloud, at some moment in time in the simulation, so 20.5 million years into the simulation, at that time we realized that the cloud was like a nearly quiescent cloud, like the pipe, for example. It had a certain value of the mass. It had a relatively low density contrast. I'm afraid you cannot see it, but here the blue points correspond to material above densities 10 to the 3. The cyan dots correspond to gas with densities above 3 times 10 to the 3, so 3,000. And the orange points correspond to gas with densities above 5,000. So there's a total factor of 5 for density contrast here. Instead, a couple of million years later, the cloud has grown. It has become significantly more massive. It has roughly doubled its mass. But now the density contrast is much larger. So now the contours are 10 to the 3, 10 to the 4, and 10 to the 5 here. So now there's 2 orders of magnitude of density contrast in this cloud. And so here we plotted the mass inside each contour as a function of time. And you can see that for every contour that we defined, we obtained increasing masses up to a certain time. And so the fact that the density contrast grows is consistent with the density profile steepening, in fact. We found that in that particular simulation. We also found it in another simulation in this other paper where we included feedback, photoionizing feedback. And in these simulations, now here we're plotting the dense gas mass within spheres of the indicated radii here. So magenta line is the gas mass, the dense gas mass within 1 parsec radius. This blue line is within 2 parsecs, the green line is within 4 parsecs, and so on and so forth, up to 20 parsecs here. Now, in this other plot, we have the stellar mass in that region. And you can see, in fact, these plots are plotted starting at the time when the first sync particle formed, so when the first star formed. And so from this time up to maybe 5 to 7 million years, we have been forming stars, yet the clouds keep growing. So that can be understood precisely in terms of this. Now, when feedback comes, because we did simulations with feedback, then the feedback just destroys the local cloud. It doesn't keep the cloud in equilibrium, it just blows it away. We did control simulations without feedback, and those just go here, and so they just continue growing. But interestingly, they continue increasing their gas mass at the same time that they're increasing their stellar mass content. This also implies that the star formation efficiency, defined as the stellar mass divided by the by the gas mass plus the stellar mass, so the stellar mass divided by the total mass, remains small even without feedback. Why? Because you're feeding the cloud at an even faster pace than you're feeding the stars from the cloud. So when we started seeing these things, we realized that accretion onto the clouds completely changes the name of the game, because efficiency is no longer the fraction of the gas mass that goes into stars. It rather becomes the competition of accretion onto the cloud and from the cloud onto the stars. And so that's what we have to keep in mind. So in summary, from this part, the density profile approaches this value of r to the minus 2, but might not reach it for reasons that we can speculate about. I can mention that later. But during the evolution, for slopes shallower than minus 2, the mass and the density contrast increase over time. And this can be the result of this gravitational choking mechanism, that the accretion rate decreases inwards if the slope is shallower than minus 2. So this is the second part of this set of works that we have been performing. Now, I would like to go into how this in turn implies that the massive stars must form later in any given star formation episode. They must form sort of at the end of the evolution of the core or the cloud, respectively. So for this, we can recall that the accretion rate across the spherical shell of radius r is given by this expression. It's the same one we had before. So again, it's the mass flux times the surface area. And this goes like r to this power, the radius to this power. But the fact that it depends on the radius means that you can calculate the accretion rate at the outer edge of a core, which you can define by some criterion. It's not a real physical boundary, it's just some criterion for defining a boundary. And you can compute the accretion rate across another inner boundary, which you could say, okay, let's imagine that this inner boundary corresponds to the region where the gas is really going into accretion disks around stars, for example. So this, and then we can compute the difference between these two accretion rates, and then we can compute the growth, the mass growth for the core, and the mass growth for the stellar component. And we will just refer to the mass inside this region as the stellar mass content of the system. Of course, I'm being very abstract here and forgetting that there are accretion disks and so on and so forth, but you have to start somewhere. So this Ri is the internal radius of this core, where we are assuming that the stars are forming, and Rc is the outer radius of the core. And like I said, then we can compute the mass in the inner part, which we think of as the stellar mass content, and that's just the integral of the accretion rate over time, but the accretion rate evaluated at this internal radius. And then the core mass is the integral of the accretion rate at the outer radius, so the boundary of the core, minus the mass that it has given up to form the stars. And this is this is a plot of what these two masses do for again for different values of this radial density profile slope, right? Because this is the parameter, the control parameter here. And It is quite interesting. Actually, we found something unexpected here. And this is that if you look at the plots for, so these are the evolution of the mass of the core and the mass in stars for different values of this exponent p. But you can see that for p equals 2 or 1.7, so a density profile of slope minus 2, minus 1.7, actually the core sort of uh, deflates. It gets exhausted, and that is because as you begin to form stars, now the total gravity is enhanced by the presence of the stars at the center, and so now you break this initial idea that you were feeding material into the stars at the lower pace than you're feeding material onto the core. But for shallower density profiles, we see that actually the gas mass, which is the solid lines, just keeps increasing. The stellar mass, which is the dashed lines, also keeps increasing. But for these values of the density profile slope, then, for example, the black lines are for p equals 1, and you can see that there's always a large advantage of the gas mass over the stellar mass. So in this spherically symmetric model, the core can get depleted, like in these two cases, because of the added gravity of the mass in stars. But for other cases, or perhaps for less stringent conditions that are not exactly perfectly spherically symmetric, or that doesn't have all the stars at the very center of the core, so the gravity doesn't peak so strongly at the center, then you can consider these cases in which the gas mass keeps increasing and at the same time that the stellar mass keeps increasing. And then if you assume a standard IMF, you can compute what is the time at which your total stellar mass is enough to form a massive star, okay? So here we're not predicting the IMF, not nearly. We're just assuming an IMF and we're saying, okay, if we have this total amount of mass in stars, when can we form a massive star according to a standard IMF? And so that is some particular time. And but at that time, when the mass is large enough, say for example, typically you need a few hundred solar masses in stars in order to form a massive star. So you could say it's around here. But by then, the core itself has also grown significantly in mass. So by that time, by the time you form a massive star, the core mass must also be large, and so massive stars must form in massive cores. And by the way, in the meantime, the core has already been forming stars. We know that we already have stellar mass in the core by that time, but you don't have to wait to form a pristine massive core, but yet starless, as was the case in the McKee and Tan theory of the turbulent core model. In this model, you expect the cores to begin forming low mass stars. They are forming stars at a leisurely pace, but then the star formation rate increases, the core mass increases, the stellar mass increases, and eventually you form a massive star, and by that time the core is also massive. So massive stars must form in massive cores. Not only that, you can also this model gives you the accretion power onto the core. And then you can look what is the feedback power from the most massive star, and then look for the moment in time at which your feedback power equals the accretion power, and at that moment in time you can assume that the accretion event will stop, and then the core will just be depleted into stars. And in fact, for example, Adam Ginsburg has a relatively recent paper, and I think now it is relatively accepted that cores can get depleted if they stop accreting. So the accretion rate, the core mass will just go completely into stars, but this is because you will cut the accretion onto the core. And so this is a plot of that. This is the mass of the star The solid lines now represent the mass of the star needed to stop the accretion. And the dashed lines show the internal mass of the core. So, and it's essentially for the same model as the previous plot, but now we're just showing the total stellar mass and the mass of the star required to break apart to interrupt the accretion flow. And so, eventually, if this is the total stellar mass, you can say that perhaps by when you are here, then you can form this massive star, and then you can stop the accretion. So this model gives you the growth and the halting of the accretion episode. And so our idea is that this is a more self-consistent model in the sense that it takes into account accretion from the core into the stars and from the cloud onto the core. And of course, it's still very idealized. I don't like the fact from this model, I'll be honest, I don't like the fact that the timescales seem to be too short. I think it's because mostly of the fact that we're assuming that we're assuming spherical symmetry, and we're assuming that all the stars are located at the center. So that means that the gravity increases very dramatically towards the center of the core. So one could think of trying to improve this model by taking into account deviations from those very strongly idealized conditions. But in any case, so this is a model that illustrates the notion of simultaneous growth of the core and of the stellar content it has. And so the summary here is that the masses in the cores and in the stars increase simultaneously, and that if you assume a standard IMF, then this means that massive stars can only form after you have collected enough mass in stars so that that you can form a massive star, and by then the core's mass itself must have grown sufficiently. At that time, the core will have been forming low mass stars for some time, so you do expect massive stars to form sort of in the late stages of a core's evolution. And eventually the process stops when you form a star massive enough to stop the accretion. And so that's that part. And I'm 45 minutes. I don't know if you want me to go into to take 5 more minutes, or should I stop here and whatever you think is better.
Do we have any questions at this moment? Maybe you can continue for
5 minutes.
5
Yeah.
minutes.
Yeah.
5 minutes. Okay,
Yeah.
perfect. Okay, thank you very much. So the last point I want to speak about is the sequential onset of collapse. And by what I mean by this is that, again, as I mentioned at the beginning, the collapse starts from the outside in, right? And then later on, the central parts begin to collapse. And we would like to get an idea of how to quantify this. How late do the central density fluctuations begin to collapse after the entire region is contracting gravitationally? So that's a goal here. And so for this, now I would like to focus on a Lagrangian gas parcel. So meaning now I'm going to follow a fixed mass of the gas, and I will follow it as it contracts and gets denser. So for now, I'm going to forget about the fact that there's accretion and that there's a continuous density profile that is more or less persistent over time. But I'm just tracking one part of that fluid as it contracts and gets denser. So when this part contracts, its mean density is increasing, and then the average Jeans mass within it decreases. So essentially, we have this thing here, this what's illustrated here. So I have mass on the vertical axis and time on the horizontal axis, and this is the Jeans mass that corresponds to the mean density of this gas parcel which is contracting. Because it's contracting, it's getting denser. Because it's isothermal, then its Jeans mass is decreasing as it gets denser. But now let's assume that this system, this cloud or whatever, contains a spectrum of turbulent density fluctuations. For simplicity, the easiest thing I can assume for these turbulent density fluctuations is that they all have the same density, and that is the typical density that you expect for the RMS Mach number of the gas. For isothermal gas, the density fluctuation goes like the Mach number squared. So I'm going to characterize the density of all density fluctuations, the mean density of all the density fluctuations, or let's say the peak density, as being given by the squared of the Mach number. But these fluctuations can have different sizes. So if I have a big fluctuation with this density, then it'll have a larger mass. If I have a tiny fluctuation with the same density, more peaked, then it'll have a lower mass. So let's assume we have a spectrum of masses of density fluctuations, all of them with the same typical density, but with different sizes. And so this is the range of masses of the fluctuations. But now if I assume that this is the mean density of the density fluctuations, then its corresponding Jeans mass is lower than the Jeans mass corresponding to the mean density. So if I have a Mach number of 2, then the density in the fluctuations is 4, 4 times the background density, and then the Jeans mass is again half of what the Jeans mass for the mean density is. Okay, so let's assume that that this is what happens. So what this shows immediately is that the more massive objects cross, or actually the Jeans mass sort of catches down, as I would like to say it, and it eventually becomes equal to the mass of the most massive density fluctuations. As it keeps decreasing, then it'll become equal to the masses of less massive density fluctuations, and eventually you reach the mass of the least massive density fluctuations. So the most massive density fluctuations collapse first. And then we can estimate the time required for fluctuations of a fixed density and a certain mass to become unstable. And I'll spare you the algebra. Basically, what we took advantage of was that Hyrides et al. Gave a nice fit for the evolution of the radius of a collapsing sphere as a function of time, normalized to the free fall time. And so we have an analytic expression for the evolution of the radius while a sphere is collapsing. So I'll spare you the math, but basically you can transform, if you assume a sphere and a certain density, you can transform the initial density, then you can transform the the evolution of the radius into an evolution of the density, and then into an evolution of the Jeans mass, and then into an equation for the evolution of the Jeans mass for the fluctuations, not the mean Jeans mass. And then you can invert this equation to get the time required for a certain mass of a fluctuation to become unstable. So this is a plot of the time required for of density fluctuation of fixed initial density, but of different mass to go unstable. This is the free fall time of the background density. But so, for example, this is all parameterized by the Mach number, as you can see here. So what this means is that for an RMS turbulent Mach number of 2, then density fluctuations of my typical turbulent density fluctuation with mass equals 1/2 of the total mass in the system collapse already at 1/10 of the free fall time. But density fluctuations with masses 0.4 the large scale mass, they take 0.7 times the free fall time to start their own collapse. Of course, when you increase the Mach number, you have denser fluctuations, and these guys can begin to collapse earlier because their densities are larger, and therefore their corresponding Jeans masses are smaller. So, But for example, for a typical Mach number of 3, which is what you expect for the turbulence, for the pure turbulence, without considering the kinetic energy in inflow motions, then you see that objects of 1/3 of a gene's mass, of 1/3 of the initial gene's mass, can start to collapse 1/10 of free fall time. So that would be one. If the global cloud is collapsing, starts collapsing at some time, then 1/10 of the free fall time later, these guys will begin collapsing. And let's see, 1/2 of the free fall time later, then these guys will begin collapsing, and so on and so forth. All right. So, of course, there's caveats. All of these calculations are highly idealized. So I used a single density value rather than this distribution. I used spherical geometry, and I assumed the free fall times for spheres, which are the shortest collapse times. So actual time scales for collapse are longer. And I ignored accretion. But this basically gives a picture. So this should be thought of as a test case or an illustration of how the onset of collapse starts later for lower mass objects. And then with that, now I will really finish. Oh, so, and this is the end. Oh, sorry, I forgot to put on my, so you see I had material for another talk, but so here's my summary, and since I've already gone a little bit over time, I'll stop here and take questions. Thank you very much.
Any questions in the room and from our online audience?
Let's see if there's an online question. Okay, then I have a question. So you didn't consider the filaments cases, which actually seem to be very common in star forming regions. So for you, if you consider the filament, do you think it will act? You kind of said that it's going to take longer. Why is that? So is it simply because you have to consider other effect, or because of more mass that you need to consider? But in the filament, there could be a very dense area that might mimic the Born-Haber sphere with some inflow. So I wonder, why do you consider that it will take much longer time to collapse?
Yeah, you're totally right. What happens here is that then there's different time scales involved. Like I said, filaments take longer to collapse. But so what that means is that you can have the central core, like a core embedded in the filament, beginning to collapse, and then an inflow. That is part of the material I didn't have time to go into, which is the anisotropic collapse. No, but essentially, what we have found in simulations of that situation, perhaps I can quickly show it here. Yeah, it's here. So basically, for example, in here, we have performed simulations of combined collapse onto a filamentary region, and which itself has a perturbation inside. And then we see this type of flow develop, which is what we had observed previously in numerical simulations. So you get a central hub, which begins its own collapse. And then you can see the arrows here are the velocity field. The colors represent the column density. And you see that there's a collapsing object. There's secondary cores forming on the filament, but the entire filament is now falling into the central part on a longer time scale. And what's also very interesting in these simulations is that, so initially the collapse is anisotropic. So when you give up the assumption of spherical symmetry, then you realize that gravity alone tends to give you first flattened, then elongated structures, like in the cosmic web, for example. So your collapse is first onto a sheet, which is perhaps the plane of this image, then collapse onto a filamentary region, and then finally the filament begins to fall into the central density condensations, the hubs or the cores. So there's a time sequence for that as well. I don't know if this answers your question. Yeah.
I think that's good enough. So any other question?
I'll go back to the
Yes, question. And Lucy.
So you were talking about how with slopes of p less than 2, it's here on the slide, accretion stagnates and you have gravitational choking. So I'm curious, within that range of the slope being less than 2, when you have values that vary, how does that change how the gravitational choking works and occurs?
Well, yeah, of course, you're right. If you allow p to vary, then you will have like a variable, like a variation on this gravitational choking. No, so your gradient, your accretion rate gradient, radial gradient, will be time dependent as well. But as long as you don't reach the slope of -2, there will be some of that effect present. And that allows for the formation for the growth of the gaseous structure, right? So to us, you're totally right. So basically, there's no need for this accretion rate gradient to be stationary over time. And if the slope is changing over time, then the accretion rate gradient will also change. But as long as there's an accretion rate gradient and that the slope is shallower than -2, you'll continue to accumulate gas in the material in the gaseous phase without being able to transport it completely onto the stellar component. One thing I forgot to mention with respect to the previous question is that, of course, we have wondered about the filaments as well. But one thing that we have realized is that the spherically averaged density profile of a filamentary object surprisingly implies a mass size relation equal to the r to the -2 slope. So the mass increases linearly with radius. And then we want to think, I mean, we have not proved this or anything, but it seems like the fact that the Poisson equation, which is Laplacian of the gravitational potential, equals essentially 4 pi g times the density, because it involves a Laplacian, that means that you have to integrate the density field twice to get the gravitational potential. And so that means that the gravitational potential is a much smoother, spatially smoother function than the density. So it seems to us, but this is just speculation, I totally admit it. It seems to us that the gravitational potential really, and therefore the gravitational force, which is its one derivative of the potential, don't really care too much about the special shape of the density field, because essentially the gravitational acceleration is like a low pass filter of the density field, if you know what I'm talking about, and then the gravitational potential is a low pass filter applied twice to the density. So it seems to us that all this spherical geometry discussion is actually meaningful, because the gravity doesn't care that much about the details of the density distribution, as long as the average is whatever it is. But so we think that the spatially averaged density distribution gives us a first approximation as to what's going on with the forces driving the inflow.
Yes, can you speak up for a question?
Sure. I think you just obviated my question.
Oh, I'm sorry.
No, that's great. But I was
thank you.
I was going to ask about those density perturbations, because, it's pretty clear that these aren't spheres and they exist in filaments. But I'll just make one comment. I think on the distributions you showed of the parallel slopes, I think I probably contributed to that over some papers over the years. And I think we're probably systematically underestimating those slopes because of the fact that when we first started a lot of that work, we were doing it with ground-based bolometer cameras. We didn't have all the Herschel data that we've had for the last decade and a half now. And
Okay.
so we weren't really considering the filamentary structure, and we were just doing azimuthal averaging. And if you have, as you're saying, with your filamentary structure, if you have things elongated more along the filament and then, more squat perpendicular to it, you'll tend to get a flatter slope in the key when you're doing that kind of averaging that fitting. But that's really
You mean
interesting.
flatter than -2, you mean?
Yeah, I mean, yeah. So if you're getting like
Mm-hmm.
1.8 being the average, I think
Mm-hmm.
that the real profiles might actually be a little bit steeper, actually in reality. But it's just because of the way that we've done the averaging in the azimuth averaging. Anytime you have something that's flatter averaged with something steeper, as you go around, it's going to make it so that it looks flatter. I think is sort of the general rule. I think yes, Urenson was the first to point that out back in a paper in 2002. But no, I find this discussion really interesting about sort of the Laplacian and applying like a low pass filter twice. You're saying the density perturbation so much. So I was interested in what the density perturbations, you kind of answered, I guess, with the previous question a little bit too about how that affects the accretion flows, and can that really help explain where streamers come from in the protostellar cores that we're seeing? So I guess that's my question.
So if you can state the question,
Yeah,
just
so it looks like that when you have density perturbations, they become enhanced. So non-spherical symmetries become enhanced during the collapse phase. So does that then help explain where streamers come from?
Oh,
Is that
yes.
sort of enhancement? Yes.
Yes, I definitely think so. When I've been talking to Griselda precisely about that, because again, this is just my hunch. This is something that sounds like it should be like that. And it's based on this idea. We know that when there's this important paper. I was going to say famous, but I think it's not as famous as it should. By Lin, Xu, and Mestel, if I remember correctly, in 1965, and they pointed out that pressureless gravitational collapse enhances anisotropy. Well, cosmologists know that because they know about the cosmic web, and they know that pure gravitational collapse on a pressureless medium like the dark matter just generates the cosmic web, right? And so here, our picture is molecular clouds are known to contain hundreds or thousands of genes masses, which means for the most part they can be considered pressureless. And in that case, then if you started out with an ellipsoidal density configuration, it'll collapse first along its shortest dimension to form a sheet, and then that sheet will collapse along its next shortest dimension to form a filament, and so on and so forth. But when does this end? This ends at small scales where you cannot neglect the gene's length or the gene's mass anymore. So this is always bounded by the gene's length. But now assume that you have this flow, and you keep feeding material into this. So this will stop at a sort of roundish structure when you reach the gene's mass. But if you keep feeding material into it, then its mass will increase, and soon it'll have many gene's masses again. And then it can start over. So my picture is that filaments in molecular clouds are formed by this mechanism. But in turn, I keep thinking, but this is something that we have not tested, and we have been talking about performing simulations connecting the hubs or the cores to the streamers onto the accretion disks. But it might be that you undergo another full sequence of these, and then the streamers would be these filamentary flows that are feeding the accretion disks. So in my mind, they're a picture of the same, a consequence of the same process. Just as you keep making the gene's mass smaller and smaller and smaller, and so you allow these anisotropies to keep appearing until you reach the scale at which pressure thermal pressure cannot be neglected anymore. So that's my picture.
Thank you.
Right, thank you. Let's thank our speaker again.
Thank you.
So stop recording.
Yeah.